All right, today we're going to be going over our pressure volume loop that we see in a single cardiac cycle. So we have our pressure in millimeters of mercury on the y-axis, volume on the x-axis. And this is like what we see, this pressure volume relationship in one cardiac cycle. So this represents, I'm going to put little points here to kind of help us figure out what's going on. Let's see, so we'll just put, this represents the AV valve opening. And so we're gonna dissect on what's going on and then different ways we can affect this loop. But so this AV valve opens, and then the blood that was in the atrium is contracting, right? And so it's pouring blood into the ventricle. So this is, we'll just put inflow. Inflow, also known as atrial systole, right? Because systole means contraction, and so the atrium is contracting, filling our ventricle. At this point, our AV valve closes. So we see an increase in volume, but no pressure. And that's because as the atrium is contracting, right, it's filling this up, but the ventricles are stretching and not necessarily having any pressure in them yet. But then the ventricles start to contract. And so we see a buildup of pressure, right? Higher pressure because the ventricles are contracting. But this is isovolumic contraction. Because in this stretch, we don't see any blood moving, right? We're still at 120 milliliters. And so no net movement of blood, but we're contracting. And then right here, the pressure builds up so much that it is eventually higher than the pressure in the aorta. And so the semilunar valve, aortic semilunar valve, opens. Can you see that? Yeah, you can. So when it opens, the ventricle is still contracting, so it's pushing blood out. We even see an increase in pressure, but a decrease in volume in the ventricle because we're sending blood away or out of the ventricle, right, into the aorta. And so this is eventually, the semilunar valve closes, because eventually we see that the aortic pressure becomes greater than the ventricular pressure, and so it closes, and that brings us to here. We got rid of all our volume, or not all our volume, right, back to 50, back to where we started. And now it's gonna relax. But as it relaxes, these valves are still shut, and so there's no net movement of blood. So this is isovolumic, not contraction, relaxation. Right, the ventricles are relaxing, but no movement of blood yet. Until eventually we receive, there's a greater pressure in the atrium than there is in the ventricle, opens and restart. This is also called ESV, this point, end systolic volume. Because at the end of contraction, or systole, this is the volume that we have. This is EDV, or end diastolic volume, because at the end of diastole, which is relaxation, let's see. Yeah, because our ventricle still hasn't started contracting yet. So at the end of relaxation, this is the volume that we have. And then we're going to start contracting, right? And these points between here And here is the stroke volume, SV. And then we're going to have an equation that we're going to keep in mind, and we're going to basically learn how we can affect cardiac output, which is equal to heart rate times stroke volume, which is what we're going to focus on most on how to affect. Okay. I'm going to erase these terms real quick, just so we have a little more room to draw what's going on next. I'll keep stroke volume. Okay, so we're going to make a line here, and as far as I understand, if we were to contract fully, relax fully and have no pressure, so if we were down to 0 pressure in the ventricle, we would still have a little bit of blood, because there's really no way to get rid of all the drops of blood in this ventricle. So no more pressure. This is still, we just have a little bit of blood. And we're going to draw a line up to this point. And this is where, remember, this semilunar valve closed. The ventricle was fully contracted and it squirted out all the blood. We got back to 50. And this is our inotropic line. Yeah, that's good for now. And so now we're going to discuss the effects of how to affect this inotropic line. So if we, basically the inotropic line tells us the amount of calcium influx in the cell and how much actin-myosin overlap that we have. So if, and that's also measuring force of contraction, right? We learned that in our last video. So if we have a greater amount of calcium, let's say we stimulated beta-1 receptors, and so we made cyclic AMP and pKa, and we have an influx of calcium. That will move this line closer to over here, because the more calcium we have, the more overlap, and it's optimal force of contraction, so we can actually push more. Whoops, that's going kind of at a bad angle. We can push more, we're here, more volume of blood out if we have a greater myosin-actin overlap or force of contraction. And we have a steeper inotropic line. And so what that's telling us, we can draw a little triangle here that kind of tells us what's going on. I'm going to draw it separate, so it's a little exaggerated, so it's easier to tell. You can still see. So if we have a slope like this, this is volume, and this is pressure. This is telling us that with the pressure that we got from contraction, this is how much volume is left. And this would be low calcium, right? This would not be optimal actin-myosin overlap. And so we do have a lot of volume left. So maybe our point ended here. And so you can see how that slope is less. I'm actually going to erase that now. But if we're here, steeper line. Sorry, this is really bad. But this pressure that we have a less amount of volume left over now, because our inotropic line is steeper. With the pressure we had, we got more blood out and we have less volume staying in. And that affects our stroke volume, because, right, this is our normal one. if we increase the calcium, we could also do this by inhibiting the Na calcium antiporter, right? So if we inhibit that, it can't get calcium back out. So we have calcium staying in the cell longer. Then, so our new line, right? If we go down, I don't know, if that 30 maybe, our stroke volume increases. And if our stroke volume increases, so does our cardiac output. So that's how our inotropic line, or an influx of calcium, can increase our stroke volume and cardiac output. Okay, next we're going to talk about afterload. And afterload, blue, can actually be seen basically at this point here. So this is afterload. And afterload is basically the pressure required to, let's see, actually, hold on. Yeah, I was on track, sorry. The pressure required to get blood into the aorta. And so our afterload is here, right? And so we trace it back. This is the amount of pressure required to push blood out, to open that valve, valve to push blood out into the aorta. And we can increase or decrease our afterload. And that can come from vasoconstriction, viscosity. If we have a smaller valve, it's harder to push blood out. So it's like the resistance the blood has to get into the aorta is another way of putting it. So if we had vasoconstriction going on, that's more of a resistance in the aorta, more pressure in the aorta. And so blood would have a harder time getting into the aorta. So our afterload increased. So if our inotropic line stayed the same, I drew kind of a new slope. That's kind of a crooked slope, but it works for this analogy we're teaching. Our inotropic line would stay the same. So we go to this inotropic line, and we kind of have a new box, right? So as afterload increased because of any of those elements that I described, we see a decrease in stroke volume, right? Instead of going to here, it's now here. So how does that affect our equation? We have a decreased stroke volume, which now we have a decreased cardiac output. Whereas if we had vasodilation, that would decrease afterload, because if we're vasodilated, there's less pressure in the aorta, or less resistance in the aorta, and so it doesn't take as much pressure to get into the aorta. So let's decrease the afterload to here. Now we only need this amount of pressure. So now we go to our inotropic line, right? That's kind of off, but that's okay. And draw a new box. Now we've increased our stroke volume. Hopefully you can see that and it's not too confusing on what's going on. So vasodilation, increased stroke volume, and now we increase our cardiac output. Okay, so next we're going to talk about preload. Okay, preload can be measured at this point here. Switch to green this time. This is our preload. And preload is basically the amount of volume that got into the ventricle. And so, or the amount of venous return is another way of putting it. So if we have a high venous return, we'll have a greater preload. So, actually I'm gonna draw this right here. So this is preload. And preload can affect cardiac output as well. So if we increase venous return, so I could start doing a bunch of jumping jacks, and that would increase the venous return. So let's say we got more than 120 milliliters out there, increased it. But our inotropic line stays the same, remember? And our afterload actually stays the same too. I mean, this is if it does, right? This is what would happen. So you'd come up here, go to the same point, our afterload's the same, and we'd kind of have like this. So these two elements are the same, but now if we go back to our stroke volume is greater. So greater preload, we increased stroke volume, which increased cardiac output. Now let's say I just sat in a chair, didn't move at all, and so my venous return isn't as good. Very sedentary, would decrease the preload. Afterload stayed the same. Same with inotropic, we'll draw it like this. Same with inotropic line. With those elements the same, we have a decreased preload. I'm sorry, we did have a decreased preload, a decreased stroke volume. So right, we just switched these arrows. Decreased cardiac output. And so that's the relationship we get with our pressure volume loop. And we can affect those three different things, inotropy, afterload, and preload. And those are our best bets for treatment of the heart, whether to increase or decrease cardiac output, whatever we need. So, all right. Okay, now I'm going to describe the baroreceptor reflex. So we have a heart. This is the aorta coming out, and these are, I don't know the anatomy really right now, but more arteries coming off of the aorta. And we have a little bulge here in these arteries called the carotid sinus. And we have baroreceptors in there. We also have baroreceptors in our aorta. And baroreceptors detect stretch or pressure, right? So in this heart, if we had an increased stroke volume, maybe an increased preload, or we have a greater inotropic line, or just greater inotropy, so it caused more blood to come out of here, or even with greater force, these baroreceptors are going to detect an increase of blood pressure in the aorta and in these arteries up close, right? And so it's going to try to do things to lower the blood pressure. It has a signal, because it stretches of a high blood pressure, it's going to do everything it can to lower that blood pressure. So there's an equation and some variables we're going to go over to help us understand what can go on. So we have MAP, mean arterial pressure, which is equal to cardiac output, right, which we've gone over already, and peripheral resistance. Yeah, you can see that. So mean arterial pressure, cardiac output, peripheral resistance. These, if we can affect these, we can affect this. And cardiac output, we learned already, go like this, that it's heart rate times stroke volume, right? And so peripheral resistance is a new one we haven't gone over, which is, I have a little bit of room there, which is basically equal to the, someone came up with this, but it's 8 times V, which is viscosity, and L, which is length of the blood vessels, divided by or over pi times R to the 4th power. Yeah, I'm gonna make that a little bigger. So these are all the factors, we can increase or decrease mean arterial pressure. So viscosity and length, if we increase them, which they have a little bit of an effect, if we increase them, we'll increase our peripheral resistance, which will increase our MAP. If we increase our heart rate or stroke volume, we'll increase our arterial pressure, or increase cardiac output, right, which will increase our mean arterial pressure. Our R to the fourth power, R is the radius of the blood vessel. And that fourth power basically means that it will have the greatest effect. So we're gonna underline that in blue, so it'll have the greatest effect. But if we have a greater force of contraction and greater stroke volume, maybe a greater preload, these baroreceptors will stretch to that pressure, and it wants to lower the mean arterial pressure. And so what it can do, it'll send a signal to decrease heart rate. Or we can change the radius of the blood vessel. And so if we increase R4, meaning we vasodilate, right? The radius is getting bigger. Then that will, because it's inverse relationship, that will decrease peripheral resistance. And we can see that, right? It's bigger, less peripheral resistance, which will decrease MAP, which was our goal, because we had a high pressure. And so we lowered heart rate, which lowered MAP, and increased R4, which lowered MAP. So that's the baroreceptor reflex. All right. Now we're gonna go over capillary exchange. And to start out real quick with a little bit of anatomy, we have a capillary sphincter right here, and it's smooth muscle. So it acts just like any smooth muscle sphincter would do. It contracts or relaxes depending on the pressure and what it wants to give, what kind of pressure of blood it wants to give to these capillaries. And it does a really good job of protecting these capillaries, because these cells, these capillary cells, I didn't really draw them. I mean, they're connected, obviously. I'll just draw them on one side. But they're super thin. And so if we have too much blood pressure coming in to this capillary bed, they'll burst. And so the sphincter will close and actually even shut completely if there's too much pressure. And then open if it needs to let blood in. We have an arterial end and a venous end of our capillary bed. And so we're going to talk about four main forces and how they drive water in and out of the capillary bed and how exchange works. And so we have a blood pressure coming in, right? From the aorta to the arteries, to the arterioles, to the capillary bed. And they go through this smooth muscle, the sphincter. And the first pressure we're going to talk about that to drive water is hydrostatic pressure. And that hydrostatic pressure in the arterial end is about 30 millimeters of mercury. And it's going to drive water out into the interstitial. Interstitial. We'll do this. Interstitial space. So because of this blood pressure, we're going to drive water out. The next thing we have blood colloid osmotic pressure. So BCOP, blood colloid osmotic pressure. And this happens because we have these proteins in the blood called albumin. I don't know what they look like, just drawing circles. But water will want to follow where the proteins are. These proteins are not permeable to these capillary cells. And so if there's a buildup of albumin here, water is going to want to come in. And that is about 28 millimeters of mercury of pressure of driving water into the capillaries from the interstitium. Our next one we're going to talk about is ICOP. We'll use a different color again. Interstitial colloid osmotic pressure. And interstitial colloid osmotic pressure, we have these proteins out here, right? Interstitial colloid, interstitial proteins. And it's going to drive water out. Water is going to want to go to these proteins. But compared to the blood colloid osmotic pressure, it's a little lower. So we're going to drive water out at 8 millimeters of mercury. Ran out of room here. I'll just drop below. Our last one we have is called IFP, or interstitial fluid pressure. So IFP. And that happens because we have these lymph vessels. And it basically creates a suction of water into these lymph vessels. It has them on up here too. I just don't have room. But it takes the excess water and a lot of waste, and the lymphatic is a filtration system. It cleans it out. And so it'll take a lot of water. Well, not a lot, but it'll take water and create kind of a suction. And so the water will leave the capillaries and go into the interstitium and into the lymph vessel. But the water leaving is about 3 millimeters of mercury. So we can now figure out a net filtration pressure that we have where water is going to. And so I'm gonna erase this. We have a little room. So we have 30 out plus 8 out, that's 38, plus 3 out, that's 41 millimeters of mercury out. And we have 28 millimeters of mercury of pressure coming in. 28 in. And so we do the math, we have a net of 13 millimeters of mercury of a pressure, a net pressure driving water out. Which makes sense because that's on the arterial end, right? And so as blood is coming in, it's full of nutrients, oxygen, and the different things that the cells need. And so we'll drive all that out. The venous end is a little bit different. Most of it's the same. So I'm gonna just write the things that are the same first. So we have our ICOP the same. So we have 8 leaving. And we have our IFP the same, 3 leaving as well. We also have our albumin, so we have 28 coming in on the venous end. Hydrostatic pressure is different though, because this is on the arterial end, blood pressure is still coming in, but as we go, we lose that blood pressure. And so by the time we get to the venous end, the hydrostatic pressure is about 10 millimeters of mercury, and that's going out, right? So that's the venous end. So we can also add up our net filtration pressure on the venous end, and it would make sense that on the venous end we need to return water to the venous end to be able to send it back through the veins and be able to restart this process. But so if we have 10 plus 8, that's 18 plus 3, that's 21. So we have 21 out and 28 in. That's 7 millimeters of mercury of water going in, right? So the net filtration pressure is an inward pressure where water is flowing in at negative 7 millimeters of mercury. And so that's how the capillary exchange works, how we get water into this interstitium. And this will bring back like CO2, metabolic waste, and stuff like that to be able to return it and filter it in the liver and whatnot. So now we're going to talk about edema. Edema is basically a abnormal buildup of water in the interstitium. And so we want these numbers to be the same in this cycle that happen normal. But things can happen where we get too great of a pressure and too much water into the interstitium. So if we have a pressure of greater than 160 millimeters of mercury coming in, this sphincter won't be sufficient and we'll have too great of a hydrostatic pressure. So this would go up, driving more water into the interstitium and would create edema. So high blood pressure would create edema. And this is interstitial edema. There's different types of edema that we won't go over. But that's one way. Hold on. Okay, yeah, I said interstitial edema, I think. That's wrong. We're talking about hydrostatic edema. And so that first example, another example of hydrostatic edema can be on the venous end. Let's say there's a blockage either in the heart or in the veins, and we can't get blood back to the heart in the venous side. And so there's a buildup, and eventually it'll build up so much or back up into the capillaries where we can't have a -7 net pressure coming in. It'll be less than that because we have such a pressure forcing back in. And so fluid will be driven out into the interstitial space again. And so those are examples of edema. In a clinical sense, if we have edema or different things, doctors can use medicine to control one of these 4 forces to fix edema, to help patients get better.